Okay, welcome to lecture 11. Today what we're going to do is we're going to look at Green's theorem as an introduction to uniqueness theorems and Green's functions. And then we're going to look at it in several examples on bounded domains and unbounded domains. We're going to look at another technique called separation of variables, just an introduction to it. We'll have other lectures on it because it's a very important technique. And finally, we'll prove the mean value theorem for Laplace's equation in 2D. So what we did in the previous lectures when we were applying what we know about the properties of analytic functions in the complex plane, and we used that to actually write down a solution to a differential equation given a boundary condition that looked like something where you had the function you specified, an integral over it, multiplied by some other function that was a function not only of the coordinates in the integral, but also the coordinates of where you wanted the solution. Okay? And we relied heavily on Cauchy's theorems over there. But that was the beginning of what we're going to try and do more generally. In other words, write down an integral expression for the answer, where we all once again have a kernel that is the function of the variables we want to know the answer at and the variables that are under the integral, and then in the integral we put the initial conditions that we have. So that was just the first taste of it. It happens to be very easy to do with complex functions because of the analytic property. But it was this idea that was eventually generalized to solving more complex partial differential equations. And I mentioned the last time that the solution we obtained was unique, and I'm basically going to prove this to you today. And the way I'm going to prove it is using Green's theorem. Okay? And it's also Green's theorem that we're later on going to use when we start writing down Green's functions, or when we start more generalizing to a greater extent this idea that you can actually write down the solution of a linear second order partial differential equation, and others as well as this integral over the initial conditions. Okay, so just to remind you of what Green's theorem is, it's valid in almost any dimensions. It's basically also known as the divergence theorem. So what we have is a domain here, and the area element is ds, and it also generalizes to higher dimensions. And its boundary is given by this curve C, and along the boundary you have a tangent vector to the curve. You have a normal to the boundary. The tangent vector I'm going to call d little s, and the normal I'm going to call n. Okay, and then Green's theorem, or the Gaussian theorem, or the divergence theorem, is simply that the divergence of a vector field A, so A is a vector field, over ds is simply equals to the integral along the boundary of A dotted with a normal of ds. So I'm hoping you've seen this before. If you have not, a way to look at it physically is simply if you have something inside the boundary and the divergence is basically the outflow of the net region is basically the flux over the boundary. Okay, so that's just an intuitive way of looking at it, but I'm hoping you've seen this before. Okay, so what we're going to do now is there are a number of corollaries that result from this divergence theorem, and it's these corollaries we're going to use in proving uniqueness. We're also going to be using it in establishing other solutions to other partial differential equations. So the first one is, let A be the gradient of a potential phi, and we simply substitute it into our divergence theorem, and what we then get is, you can see where the Laplacian is coming out, the integral over the domain D of the Laplace of phi ds is simply equals to A, which in this case is now the gradient of phi dotted with n times ds. Okay, and the gradient of phi dotted with n is simply the normal derivative in the n direction. Okay, so here you get definitely the picture of the divergence over the domain is simply the flux as you go out. Okay, so that's the first identity we're going to use, and I'm going to color them and label them because they'll appear subsequently in the later things. Okay, the next one is, let's let's consider two functions, and here we're starting already with the building blocks of where we're going to do this complicated integral. Let A be some function f times the gradient of another function, and we substitute that into our divergence theorem over here, and what we're left with is, first we're going to work out the divergence of A, and that's simply applying the chain rule to this thing. So we're going to have that the divergence of A is the gradient of f dotted in with the gradient of g plus f times the Laplacian of g. Okay, so that's just the divergence of A. We then put that into our divergence theorem, and we want to find an expression for this beast. So this is simply substituting divergence A into the divergence theorem. So we get that is then equals to f, which is basically A. So it's A dot n over the boundary. So it's simply f grad g over the boundary. And that's equals to the result we're going to use. It's simply f times the directional derivative of g on the boundary. Okay? So that's a direct corollary of the divergence theorem. Let's make another one. Specialize the above case if f is equals to g is equals to some function u. And what we then have, simply substituting this into the expression above, we have grad u dot grad u plus u times the Laplacian of u ds is equals to u grad u dotted in with a normal to the curve that we're integrating over, and we have that expression. Okay, so also just the corollary of the divergence theorem. Now we can do one last thing that we're going to need is we're simply going to say, let's take number 2 again, and let us consider another one, number 2, but we've switched f and g and we subtract the 2 from each other. Okay, so subtract the same equation but with f and g interchanged. And the reason we do that is the moment we subtract the equations with f and g interchange, we get rid of this term. Okay, and so we basically have f grad g minus f Laplacian g minus g Laplacian f is equals to the difference of the flux on the boundaries of the two interchanged. So that just came from there, which is also equivalent to saying f times the normal derivative of g with respect to n minus g times the normal derivative of f with respect to n. Okay, so all these colored bits 1 through 4 all are simply consequences of the divergence theorem applied to different cases, and you're going to see how useful they are as we go on. So the first thing we're going to do next is prove the uniqueness of our solutions we found. And what we're going to do is simply use the corollaries that we got from the divergence theorem in the following way. So let's say, suppose we have a domain D, and we have two solutions to Laplace's equation, u1 and u2. And we now want to prove that those two solutions are the same thing. What we're going to do is, okay, so there's a Laplace's equation, u1 obeys that, and it's going to be more than just Laplace's equation. It's going to be Laplace's equation is equals to a source. So we've generalized it a little bit, and the reason for that is we can actually prove uniqueness for that more general case as well. So we're going to say the Laplace of u1 is equals to g, which is a function of the variables on the domain D, and the Laplace of u2 is also equals to g, so they obey the same equation. And we're also going to say that u1 is equals to fxy and u2 is equals to fxy on C. Okay, so we have two solutions obeying exactly the same Laplace equation with source and having exactly the same boundary conditions, and we want to know whether it's possible to get two different solutions. And the way we do that is, just one comment before I go on. If you specify u on the boundary, we're going to call that Dirichlet boundary conditions. It's just the definition. It's after the guy who explored the consequences first. Okay, you'll see that there are other possibilities actually as well. And So anyway, so we're going to have u on the boundary, and we're going to have u1 on the boundary, u2 on the boundary, and that's what I call Dirichlet boundary conditions. And we're now going to say, let's parameterize the difference between u1 and u2 by u, and we want to effectively show that that thing is zero, identically zero, both on the boundary and on the domain inside. Showing it zero on the boundary is easy because we know they are both equals to f on the boundary, so the difference is just going to be equals to zero. But the tricky part is to show that u is actually vanishes inside the domain. Okay, we know that u obeys, because both u1 and u2 obey this thing. If you subtract them, u obeys the Laplace equation on D. And u is equals to 0 on C, on the domain. And what we're now going to do is we're going to use that third identity that we derived when we, it looks like this one, okay, when we had A basically equals to u times the gradient of u. Then we got this expression, and we're going to substitute what we know about u into this expression. And so what we're going to get is the gradient of u dotted with the gradient of u plus u times the Laplacian of u, which we know to be 0, as well as u times the normal derivative of u on the boundary, which we also know to be 0. Okay? So we're left with this expression. And if you look at this expression, you can see that this is a norm of the gradient. So if you're working in Riemannian geometry or any example that we've looked at, that norm is always positive. In other words, for the examples that we were looking at in the previous case where we had uxx, where we had just two variables, we have the gradient of u is simply ux and uy dotted with a gradient of ux, uy. And so we simply have that is ux squared plus uy squared. So let's just write that down. So this integral is then equals to that, and we know that that thing is equals to 0. And the argument now goes, because it's the sum of positive valued functions, positive of 0, this thing can only be 0 if every single component is, and it's an integral, of these things are 0 everywhere on the domain. So this integral being 0 implies that ux and uy must identically vanish on the domain, which basically tells us that the function u is a constant. Okay? U is a constant everywhere over the domain, but we know that on the boundary u is equals to 0, therefore the constant has to be 0. Okay? And so we've effectively proved u is identically 0 on both C and D, and therefore the two solutions are the same. u1 and u2 are exactly identical, which gives us the uniqueness theorems for the Laplace equation. This derivation is valid even in higher dimensions, because you just are adding more, like uz squared or whatever. So it's exactly valid. So it's true for Laplace's equation in any dimensions. You can simply verify directly for 2. Okay, a very powerful technique, a very powerful statement, because it means that whenever you found a solution that satisfies the boundary conditions and the equation, you're done. Okay, you have to do no more. And that's what we did in the previous lecture. We found a solution using Cauchy's theorems that actually satisfied the Laplace equation in 2D. Okay, so now the next step is to look at a generalization of the boundary conditions. We've looked at the case where we specified u1 and u2 on the boundary, but you could also have specified what the derivative of u1 is on the boundary, or what the derivative of u1 is on the boundary. The difference would be, and it's entirely physically motivated, suppose you have a wire frame, okay? What that would mean, if you were specifying u1, you would simply specify the height of the frame, say, on the x-axis. If you would specify the derivative of u1, you wouldn't be specifying the height of the function, but you would be specifying the gradient, how the function leaves the boundary, and then the equations would be free to adjust the height of the function. Okay, and depending on your physical problem, you have both possibilities. In fact, you have a third one as well that I'll treat as well, but you only have those. So let's look at the consequences of what they call Neumann boundary conditions. Okay, so Neumann boundary conditions is once again named after the dude that explored them first, and it basically means that on the boundary you specify the normal derivative, in other words, how the function changes as you go over the boundary, but not necessarily its value. And you give it you're saying that it's a function of g, which is not the same g, unfortunately. It's a bad choice. And you can say this normal derivative is also specified in the same way. So you once again are looking to prove the uniqueness theorem. So you have two functions that obey the same boundary conditions and the same and Laplace's equation. And so in this case, you have that the difference between the two functions is normal derivative is 0 on the boundary. And you can then have, again, that our third identity from the previous slide implies this. So you once again have this gradient squared term plus u Laplace squared of u, which we know to be 0, plus the second one of the boundary term now becomes important. So we have that these two vanish because of the Laplace the equation with source being the same and the initial condition being the same. And you're once again left with the statement which then directly implies that u is a constant, but that's all you can say. So you cannot say it's 0 because you have not specified the function on the boundary. So the uniqueness for von Neumann boundary conditions is you can define the function up to a constant. Okay? Which makes sense because you've said you can always find the function leaving the boundary at a certain gradient, but that will be true whether you add a constant or not. Okay, so that's the uniqueness if you have von Neumann boundary conditions. There's another type of boundary conditions that you can specify. You can say, suppose on the boundary you specify the normal derivative plus some combination of some constant times u. In other words, it would be the case like suppose you were solving a flow of a pipe, right? You would say the larger the velocity of the liquid is, the faster it flows. Okay, so that would be an example where you use a boundary condition like that. They call it a Robinson boundary condition. Okay, I didn't write that down, but that's what it is, and it's just the final type. So you either specify the function, which is Dirichlet, or its derivative, which is Neumann, or a linear combination of the two, which is Robinson. And for this case as well, you can now go ahead and you can then work out the uniqueness theorem for that one as well, and it goes very similarly. So for the uniqueness theorem, you once again have identity 3, which implies this thing is equals to this boundary term. But we now know that none of these guys independently vanish because we know that they obey that equation. However, what we can do is we can substitute this gradient in there. And then what we get is that the gradient is equals to minus mu u. So we move it to the left-hand side, and we simply have an integral over squares times ds, which comes from the norm squared of the gradient, plus the integral of mu times u squared. And we note that in this definition of the boundary condition, I've conveniently put u equals positive, which is the only place where the theorem actually holds. And so we have this thing, which is a constant times a positive thing, which is squared, which is also going to be integrated. And this thing only vanishes as if every single positive quantity under the integral sign is 0 everywhere. So we once again have that ux, uy is equals to 0, so it's a constant function. And from the boundary integral that we have that u is equals to 0 on the boundary, and so uniqueness follows. Okay. Very powerful. So for all these three conditions, all you have to do, depending on the boundary condition, you have to find a solution, and then you know you've got the unique one. Okay. The last thing that we have to prove, and the main reason I put this one in is not to be completely tedious, but it's unique for everything depending on, irrespective of how the boundary is actually specified. So up until now, we've been looking at everything inside a specified boundary, but you could do the same thing on an unbounded region. Okay, so consider the following thing. You have an unbounded domain, and you have u1 and u2 specified, functions specified on that boundary. So you have this situation, okay? So you have a boundary over here, the blue boundary, u1 and u2 are specified there, and you're interested in what the function looks like outside. Okay, and places where you actually get this problem a lot is, suppose you have the Earth, and you're interested in what the gravitational field looks like outside the Earth and extends to infinity, then you have this problem, because the boundary is then just the Earth's surface. Suppose you have something that's charged, like an electric conductor or an electric ball, and you're interested in the electromagnetic field potential, say, outside the electric ball, and so you once again have exactly this problem. So this is why we're interested in it, and it's just technically slightly more complicated, but it's exactly the same thing. So for this case, we're clever. We're still going to use Green's functions, except that we're going to look at the Green's equation or the Green's identity on this whole domain D, and we've now made the unbounded domain a bounded one if we integrate along this whole contour, right? So we integrate along that whole contour and out there and then round the purple side and all the way back, okay? And then these things, you basically take these lines on top of each other, and because you're traversing the one out and the other one in, those two contributions cancel. So it is kind of, you used the same techniques when you looked at residue theorems in complex analysis. So let's write it out, and the question that we want to answer is U unique on D outside C, so in this outside region, and we're going to apply Green's theorem to the full contour, and we know that U1 and U2, this difference between the two is equals to 0 on D, and U is equals to 0 on C. So I'm just going to do the Dirichlet case. All the others follow the same way. It's the same techniques. The only thing that's new is now dealing with a contour, both contours. So what we then have is that using 3, which is the same identity we've been using, we simply have, once again, that these the norm squared of the gradient plus U Laplace squared U ds is equals to the term that comes from going around C, okay? But just to remember, the direction in which you go around the contour is important, right? If you change direction of your contour, you flip the sign. So if you'll note this picture, we're traversing the contour in a different way, so we have a minus sign in here, okay? Then we go out, and then this guy we transversing this contour in the counterclockwise way, so then it's our positive sign. So we have 2 contributions over here, and the contribution over these 2 lines exactly cancel because they're going the opposite ways. Okay, and so we now know, because of our boundary condition, that this one in the interior vanishes, and we are left with this expression. Okay, so we have that our Laplace squared on the domain of interest is equals to the contour on CR, which is this outer contour, okay, and multiplied by this factor over there. And so it is now this thing that we have to evaluate, and that's a little bit more tricky, but it's actually very, very interesting to do. So before I evaluate it now, I'm going to introduce that technique of separation of variables for the first time, because it turns out that you can actually write down the solution for big R in a systematic way, and we're actually going to use that to show you that this term ultimately vanishes. Okay, so store this idea. We're doing the uniqueness theorems for the Laplace equation on an unbounded domain. We need to evaluate that integral, the one over here, at infinity to be able to prove the uniqueness, and we're now going to develop the machinery to do that. Okay, so what I'm going to introduce now, and I'm going to come back to it because the very powerful technique is separation of variables. In fact, generally, it's the first thing I try, because if you can achieve separation of variables, you instantaneously change your partial differential equation into two separate ordinary differential equations, which you can then solve. This is something that basically drove most of the differential equations, ordinary differential equations, second order things that we've solved, is due to the fact that they originated in separation of variables. Okay, so most of our 19th century, early 20th century, and most of Baderman's equations that you bothered to solve actually come because they found themselves appearing in physical problems that people then explored. And they're like famous functions like Bessel functions, Legendre polynomials, all those things often appear in as a result of separation of variables. So I just want to give you an idea of what it is and then use the result for proving the uniqueness theorem over there. Okay, so let's look at possibly the simplest example. We have Laplace's equation is equals to 0, and we're going to change variables to polar coordinates. Okay, so we're going to say r is equals to x squared plus y squared, and tan theta is equals to y over x. And by this stage, you should be quite fit in changing variables of a second order equation. So I'm just going to give you the result. Okay, so work through it. Make sure you know how to get from uxx plus uyy equals to 0 to this expression. Okay. So this is Laplace's equation in polar coordinates. And now the approach is going to be, let us suppose our solution, we can factor the solution. Okay. This is ansatz. There's no reason that the answer should actually be in this form, in these coordinates. But if you found one and the answer is right, you know that it's the right one. So what we're going to do now is we're going to suppose the solution has this form, substitute it back into our Laplace equation in polar coordinates, and then work out the consequences. Okay, so you can see this first term of r squared times urr is simply the second derivative of r, and because we factored u, it's simply the second derivative of r over there. Okay, times theta of phi times r squared. Okay, the second term is simply r times the derivative of u with respect to r, so it only hits the r function, so you have theta times r prime, and the last one is simply the second derivative with respect to theta, and then you have the function of r times theta prime, the second derivative of the theta function with respect to theta. And now the next step is divide by r and theta, okay, and then rearrange the function. Okay, so if you've taken this expression, divide by theta, so this thing divide by r theta will simply give you r squared r double prime r over r, which is that term, and divided by theta cancels that guy out, dividing by theta cancels this guy out, and you're left with r prime over r, and that must be equals to theta double prime over theta. And now the thing is that on the left-hand side you have a function only of r, and on the right-hand side you have a function only of theta, and this equation must remain true for both for any r and theta, so it only can be true if both of them are equals to a constant. Okay, so it can only be equal if each side is equals to a constant. Okay, because the functions vary independently, and so you must have them both sticking to a constant. And this allows us then to split this equation that comes from the partial differential equation in two unknowns into two separate equations that are just ordinary differential equations. Okay, so let's call the constant n squared. You can call it absolutely anything you want. And so we have that theta prime over theta is equals to minus is equals to n squared. And so you write everything on the same side, and you have theta prime plus n squared theta is equals to 0. And you also have that this part was equals to n squared, and you multiply through by r, and you bring everything to the left-hand side, and you're left with this equation. So we now have two ordinary differential equations that you can use if you find their solutions to construct the original equation u, which is an equation of two variables. People have become famous for finding coordinates in which the equation is actually separable. Okay, and in fact, a very famous guy in the field of gravitation is Sol Tukolsky, who's actually South African. He managed to solve the wave equation around a black hole, or find a way of separating the wave equation around a black hole that made tremendous many calculations possible. In fact, a lot of the analysis that the big experiments in gravitational wave physics are doing is simply because of his clever choice of coordinates that showing that you could actually find the answer by separating variables. Okay, it's sort of the way in our field often that you can become famous, and it's basically that solution allowed him to get a very good job early in his career at Cornell University, and he's become one of the really big guys in the field of gravitation and in numerical analysis as well. He wrote one of the big books. It's called Numerical Recipes. If ever you want to write computer code that actually evaluates functions, it's the place to start looking. Okay. So South Africans can do this very, very well, some of them. It's a skill to be able to do it. Okay, so let's now solve these equations. Okay, so the first equation is simply theta, two derivatives plus n squared theta, and that's your harmonic oscillator. So you can integrate that twice, and you can show that the unique solution is simply constituted out of two independent solutions times, which is for a given n. So you have an cos n theta plus bn sin n theta. And the second solution is, and n can be any constant, right? Because theta goes, you need to have it periodic in 2 pi because we're dealing with polar coordinates. So theta is any integer. It should be, there's a mistake. Oh. It should be cos of theta over 2. It depends whether you're working in polar coordinates or not. Anyway, it should be such that when theta is 0, that is cos is equals to 1 when theta is equals to 2 pi. So there's a factor of 2 pi missing there. I apologize. Okay, because it has to go round and it has to be periodic in theta. Okay, fortunately we're actually not going to use this guy. So the second equation is the r equation. So you have r squared, the second derivative of r, plus r times r prime minus n squared times r. I'm hoping you solved these type of equations in the second year. What would you do? Guess.
First, divide by r squared.
You could do that, but the way I looked at it, whenever you take a derivative with respect to r, you lose a power of r. Okay? And so here, this r squared is actually fixing it. So the technique I used is that you basically assume that you have a power series in r. So you make an ansatz that r has this form, you put it in there, and then you find out what alpha is to find a solution. Okay, and it only works if the power that you're multiplying the derivative with is the same, or there's a common factor between all of them. Okay, so this is basically a guess. Okay, it's an ansatz. You put it in, if it works, and you can find a solution, then great. You know from your theorem of ODEs, because it's a second order ODE, you always have two independent solutions. Okay, so you make that ansatz, you check, and so when you check, you have that R here is just R to the alpha. Okay, oh, wait, let's look at the first two terms. You have this one, the two derivatives of R times R squared is alpha times the derivative of R to the alpha minus 1 times R to the alpha minus 2 times R squared. So that's your first term. Plus R's first derivative, which is just alpha times R minus 1 times R. So that is alpha R, R to the alpha minus n squared R to the alpha. Okay? You can factor out R to the alpha and then simplify things, and what you get is that alpha squared minus alpha plus alpha, so that falls away, minus n squared is equals to 0. So you have that alpha is just equals to plus minus n. Okay. Okay, but the only thing, and here comes the fact, the difference between the previous proofs. I'm going to assume that R is bounded. In other words, I'm going to throw away all the solutions in this proof that explode at infinity. And so instead of having two independent solutions, I'm simply going to choose all of them we're basically going to throw all the ones away in which alpha is positive. Okay, so I'm going to basically, in this proof, basically assume that my solution is bounded, and my phone is being annoying. Okay, now it's shushed. And then throw away all the other solutions. And so I'm basically going to have alpha taking on values 0, minus 1, minus 2, etc. And so the moment I do that, I can say that U is equals to A1 over R cos, okay, but now theta is going to be theta over 2 pi, which is what I forgot. So U is equals to A0 plus A1 over R times cos of n equals to 1 times theta over 2 pi plus sine of n equals 1 times theta over 2 pi times B1 over R. And you can write down the higher order terms, but we're going to evaluate this function as R goes to infinity. So those higher order terms are going to die off further. Okay. This type of thing where you can write down the solution on the outside of a domain as a series in R is not unique. It appears often. I mean, if you look at the Earth, they call it a multipole expansion in physics. You have this dominant term, which is just like the 1 over R potential. Then you have higher and higher and higher terms in R. And as a very good approximation of the Earth, it's just a sphere. Okay. When you have rotation, then you have the R over squared term coming in. And then if you want to describe mountains on the outside of the Earth, you get higher and higher R terms. But far away, this Earth basically looks like a sphere. And the same thing is true if you look at electric charges, which is why suppose you have a very clumpy shape. Okay, close to it, you can actually have a weird electric field, but far away, it's going to just look like a point charge. Okay, it's one of the features of the solution that actually is bounded at infinity of the Laplace's equation. Okay, so we have this. So now, using this argument from separation of variables in polar coordinates, we've shown that U can be written as a power series expansion in R, provided we have assumed that the solutions are bounded. Okay, so we're now going to put this back to finish our theorem on the unbounded region. Okay, so we're going to say this theorem is basically considering our unbounded region. We have the boundary conditions on the inner side, like the surface of the Earth, and we tried to answer this question, and we wrote down this integral over here, and we now are in a position to try and evaluate what this integral CR actually is. In other words, evaluate the function over there. And we're going to use our separation of variables result to get the dominant term as we're moving to infinity. And there's our result that we get. And so asymptotically, you're going to have that u is equals to a constant a0 plus some terms 1 over r. And you're going to have that the derivative of u on n, the normal derivative, and n here is simply in the r direction. Okay, so it's simply du dr is equals to something that goes like 1 over r squared, right? The constant disappears, you take a derivative of 1 over r, so you have 1 over r squared. And so what we do now is on that boundary, as r is going to infinity, we have that du dn is simply smaller than, because the causes and the sines are bounded, okay, is smaller than the absolute value of a1 plus the absolute value of b1 over r squared. Okay, and important here, we have made the assumption that u is bounded at infinity. So the uniqueness theorem in an unbounded region requires the assumption that u is bounded, because we threw away all the unbounded solutions. So if u is bounded at infinity, we have that this limit behaves as follows. You basically want to compute the limit as r goes to infinity of this integral along the boundary, and we're now going to put in our estimates for these functions to obtain an upper bound, and we have that. So we know that that integral is less than or equals to this thing, and we now have to evaluate this integral. Be careful whenever you're working here, this ds is got to be the parameterized along the curve. So it's basically r times d theta. So there's a hidden factor of r sitting in here, but that's okay because we've got two factors of r over there. Okay, so let's now take it from the integral on the boundary, which in 2 dimensions is just a contour integral. In the complex plane, we write it in terms of real variables, so it's from 0 to 2 pi a0 times this constant over r squared times r d theta. Okay, so you multiply it out, you compute the integral, so that's just 2 pi times, because r is a constant, assumed to be constant over the integral because you're integrating over a circle, the r cancels out with one of the r's over here and you're still left with 1 over r, which is essential, and the limit as r is approaches infinity for 1 over r is 0. Okay, so we have that this integral on this right-hand side across the circle is bounded by 0, and therefore you have that this thing is equals to 0, and thus the result follows. So that norm, the norm squared is identically 0, which implies that u is a constant, but in the case of Dirichlet boundary conditions it's 0, so u is unique on D. Okay. So uniqueness then follows basically from Green's function, as well as the assumption that asymptotically the solutions are bounded. Okay, and you can do the same thing whether you have the other boundary conditions, because all the things remain true, and this inequality system also remains true. So you're done, basically. Okay, so I'm going to conclude this class just by an interesting result for Laplace's equation. They call it the mean value theorem, which actually came as a surprise to me. It's not an obvious result, but it does give you the idea that a certain class of partial differential equations will give you very unique surfaces, right? It's not like the solutions of Laplace's equation is just not any surface. There's certain surfaces that can be the solutions of Laplace equations, and the others that just can never satisfy Laplace's equation. And one of the main things that helps us identify it is this idea of the mean value theorem. It's also useful later on in making proofs. Okay, so the mean value theorem is something like this. Let's define what a mean value is before we make a theorem about it. So I'm going to define the mean value at any point P on the solution as follows. Okay, in some sense, I'm going to take the solution at point P. I'm going to draw a circle around it with radius r, and I'm going to say the mean value at that radius is simply the integral around the circle of all the values of u. Okay, so I'm basically, even though, suppose I have like a surface that does that, I'm going to pick a point P, I'm going to put a circle around it, and then I'm going to integrate around this circle. I'm going to say that is the mean value around point P for that radius. Okay, so that's exactly what I've defined now. And now the theorem results is if I take this derivative. So I'm going to see how this mean value changes depending on the size of the circle I choose. Okay, so depending, just from the definition there, potentially you could have different values depending how big the circle actually is. And so let's work out what the derivative of W of R is with respect to R using just this definition. Okay, so the derivative of W with respect to R is the derivative of U with respect to R times d theta. Okay, because it's basically R just enters there, and you simply have to take the derivative. Okay, and so it's effectively the gradient of U dotted in with the normal of around the circle times R d theta. Okay, those two equivalent. Do you feel comfortable with those expressions? If not, you must get yourself comfortable, and you must come and ask me when you get stuck or what confuses you, please. Okay, so just that UR I've rewritten as R times d theta times 1 over 2 pi r. So these two r's cancel out, and UR is just du dn. Okay, and the reason I did that is I want to get back to Green's theorem. Okay, so that I can use it and I can work out the consequences. So this r d theta is simply ds if you're going around a circle. So I simply have partial u partial n ds times 1 over 2 pi r. Okay, notice up until this point I have not said anything about the surface I'm defining the mean value for. Okay, so what I'm going to do now is I'm going to specialize to looking at surfaces that obey Laplace's equation and work out what happens to the mean value in that case. So remember, on the first slide we had that expression 1, where we had placed A is equals to the gradient of phi, and here I'm going to simply say that phi is u. Okay, and then what we got was this expression from our divergence theorem, that the integral of the Laplace of u ds is equals to du dn on the boundary. And so if you obey Laplace's equation, this thing is 0, and as a result, so is that thing. So we now have the situation that this integral also vanishes, and so you have the derivative of w with respect to r is equals to 0. And that is a very powerful result, because it basically means w of r is a constant, and that constant is the same. So a solution of Laplace's equation, you can immediately check if somebody gives you a physical one, is you pick any point, you work out the value, the integral of the value of that surface around that point, And if it's the same for various radii for all points, then you have a solution to Laplace's equation. It's a very easily verifiable property of Laplace's equation. Okay, so this mean value, which is the integral around every single point, is constant. And moreover, that constant, it's valid even as r approaches 0, so it's equals to simply the value of the function at the point. Powerful, right? Any surface that obeys Laplace's equation, pick a point, work out its value, and then you're guaranteed that the average value, as the circle gets bigger and bigger, remains that value. Okay, it's kind of nice. And there's a lot of, I mean, we're doing partial differential equations as solutions, but there are a lot of people that have actually solved solutions to specific problems. Like, this is Laplace's equation, there is the minimal surface equation that you have in the next problem set. And there are properties to these surfaces that you get that follow from the differential equations, that follow from where they appear in physics, and you eventually get fit and you know them. And you see their properties in other places, and then it also helps you when you build models. Okay, but for now, we're just going to derive this thing, so that's basically our mean value theorem, and we're going to use it later on in proving other things. So there are a couple of properties of surfaces that solve Laplace's equation, but also of elliptic functions in general. Okay, and in the case of Laplace's equation, we're going to use the mean value theorem to actually prove some of these properties in the next lecture. So questions about this? Oops, it's the end of the story. Questions about this? It's a cute result, and then next time we'll go on. So I think I'm going to stop recording for now. If I can get my cursor back. Sorry.